This is the outline of the talk. So typical problem for industry is that many tasks have to be, what can I say? People want to know if it's doable, what you're saying you can do or not. And you need to see upfront how could a result look like if you go there and collect data. Good for us is that some models in the industry only require a smaller set of functions. You don't need a full 3D visualization for many of these tasks. And another motivation was that many users are not really familiar with file scripting and want an easy access to a model. So we decided a GUI that connects between users and gprMax would be very useful. And because we are usually working with smaller computers like PCs, we decided we focus on 2D. 3D requires quite often a knowledge of details, which is upfront not always available. And last but not least, it requires a bigger computer. So we wanted a GUI that provides an easy way to simulate essentials of subsurface 2D. Previous work we made already for the 2D version of gprMax, a version written in Scilab. Originally, gprMax was designed to run with MATLAB, and we chose Scilab because it was open source and very transparent in all parts. Then the new GUI came when the Python version was released, because the other stuff didn't run anymore. So the GUI we made was written with the tkinter tools in Python. It works in the same directory as gprMax. Script input files for use in gprMax include antenna parameters, media parameters, and geometry input. Automatically calls the gprMax functions for running the simulation of the model and for displaying the results. And when necessary, functions were adapted. So when we are setting up a new project, it works from scratch or from an already existing one. You will soon see how that looks in detail. This is just listing. Defining antenna properties with artificial or real waveforms is the second step. Then we include up to 18 media with individual properties. Then we draw the subsurface with click and drag. 4B could mean we could also look into the file that gets written by doing this, which is the ASCII control file. We look with editor in, and might be interesting for us to adjust little details in the ASCII file with the editor. Then we can make a first trial with the A-scan. If this runs smoothly, then we start the B-scan simulation. And last but not least, we have display radiograph, where we can apply some gain or interpolate values for getting smoother images. So when we call the GUI by clicking on an icon on the screen, we get this main window, which includes settings, antenna, media, geometry, simulation, display. GUI settings include location of the project, and location of media file, antenna file, geometry file, color map file. Important is that this is selected properly. If things exist already, then it's already filled with information. For new projects, we have in principle 3 columns. New information, you want to use existing and or new information, and there's new information if this is needed. The antenna GUI includes the time window length. The source can be any prefabricated like Ricker, Gaussian, and so forth, or user. And with user, you can include a user function, means something that you collected from real radar sections, from real radargrams, antenna wavelets, which could be built in here. And in this, you have also a function for smoothing and optimizing the function which you collected from a real radargram. As you will know, edges or jumps or any discontinuity would lead to unpredictable results. You need to have a smooth wavelet here. Amplitude is normalized, maximum is 1. You can have it smaller or 1. Frequency, transmitter, where it starts in X and Y, the step and the offset between transmitter and receiver. This is, for example, the GUI that deals with user wavelets. This is collected from real data. You could also use tapering and smoothing and calculate the result. If you have no jumps or discontinuities at the edges like here, it will work reasonably well. The media, which is very similar to the older version, that's a table containing all the material properties, which will be used here in the geometry GUI, where you have different materials from the table. You can also load more. And you have an object manager where you can move up and down objects. You can define objects, plane, box, circle, rise, radius, and so forth. Different colors for different materials. And then you draw what you need to set up, like in a drawing software, and assign the electrical properties. In the options menu, when radargram has already been built, you can decide if you want gain on the amplitude, if you want a color table in gray, or we have also red and blue, the classical seismic colors, interpolation with different processes, Hamming, next neighbor, and so forth. Zero centering deals with the grayscale, that the zero is symmetrical to the peaks, plus minus. Data bounds can be used, or you use a minimum or a maximum that you define. This is all, in principle, visualization part. So here I'm supposed to show the video. I hope this works smoother than the other part. Complain loudly if this doesn't work. So after clicking on the icon, the main menu opens. You can adjust settings. For new projects, the 3-column version. And input conversion, when you collect something that you digitized from somewhere. Media, geometry V-scan. It's now squeezed in a shorter time. Normally this takes between 10 and 20 minutes. For the kind of example which I'm displaying in a few seconds, you see all the steps. Now we want it a little bit smoother. Grayscale. And now we just look on the radiogram. Now it's smoother in grayscale. Now we want more gain. Now the deeper parts are more visible. If this is not enough, there's one more. Up to 5, we worked on this data set. Now it's even stronger, the reflection from the back side of the sample. Okay, that was the video, just showing typical application, a wet delamination on a paved road, top layer, wearing course, typical thickness 4 centimeters. Here you see the simulation of delaminated part, which is moistured with a 2 millimeter layer of moisture. And this is how a result looks like when you use our 2D modeling. This is where the moistured part starts, and this is the dry side. And if a little bit more gain, it's a little bit clearer what happens here. And you see multiples. And another example, a back wall behind 2 layers of rebar. Question was, with different material between concrete and bedrock, how looks the back wall response through rebar, 2 layers of rebar and different materials here. That's the model result. You can see here the one part reflects more significantly than the other side. The question was, is it detectable at all in this case? So I can already conclude we don't need console input. We have visual access for gprMax modeling. It's comparatively easy to run the 2D models. We can provide gain and smoother interpolation for radiograms so that some people think it's looking a little bit more like a real measurement. This GUI connects between the 2D users and gprMax. Typical survey missions can be assessed for feasibility, and companies save money by avoiding not suitable surveys. And thank you to the gprMax team that this is doable and possible.